Welcome to the third installment of the Reservoir Sedimentation Management series. This series is sponsored by the Cooperative Institute for Research in Environmental Science at the University of Colorado Boulder. Today's talk is called Sedimentation Management for Multipurpose Reservoirs, a Federal Perspective. The talk will be given by Dr. Tim Randle at the U.S. Bureau of Reclamation and Dr. Paul Boyd at the U.S. Army Corps of Engineers. Tim is the manager of the Sedimentation and River Hydraulics Group at the Technical Service Center at the U.S. Bureau of Reclamation. And Dr. Paul Boyd is the sediment representative for U.S. Army Corps of Engineers on the Subcommittee on Sedimentation for the Advisory Council for Water Information for the U.S. With that, I'll turn it over to Tim.
Well, thank you, Toby, and thanks for all the people that have joined in to participate. This will be on sediment management for multipurpose reservoirs, a federal perspective, at least from two federal employees. So I just wanted to remind folks what sediment is. Some people confuse it with sludge. It's really not sludge. It includes clay, silt, sand, gravel, cobbles, and boulders, and this happens to be a photograph of the Elwha River that shows a wide range of grain sizes. So the existing practice in the United States and much of the world has been reservoirs are functioning as originally authorized and designed, which also means they trap sediment. The trapping of sediment was something that was always planned, but people may not be aware that the numerous benefits provided by the nation's reservoirs are not sustainable over the long term without some kind of sediment management. So the old best management practice, sort of a no action, just let the reservoir eventually fill with sediment, and hopefully before you retire. But that poses an intergenerational inequity issue. So if you think about this in terms of generation, it takes about 20 years or a generation to conceive, plan, design, and construct a dam and reservoir. And then the next generation starts receiving the benefits. They're repaying the capital cost, and they're also paying the O&M cost. And usually at that point, sedimentation is not a big issue, so nobody worries about it. And then the third generation comes along, and they're continuing to receive the benefits of the project. They're still repaying the capital cost and paying the O&M cost. Again, really not paying much attention to sediment in the reservoir. And then the fourth generation is kind of where we're at now. The capital costs have largely been paid off. So they're paying the O&M and still not really paying a whole lot of attention to sediment management. And then eventually the last generation realizes that the sedimentation have posed insurmountable problems, and they're stuck with the retirement bill, and they have to develop new water storage at higher costs. This has happened at San Clemente Dam in California and also Matella Dam in California.
All right, Tim, I'll take it over here for a few slides. As Tim noted, the old best management practice, and where does that get us, and where do we sit if we say we're in that fourth generation right now, and we're looking towards maintaining our O&M, but not really investing in our sediment management. Where does that leave us? And this is a plot that I pulled from our reservoir sedimentation information database that the Corps and the Reclamation have been putting reservoir data into. And you can see this extends from 1910 to 2017 here. And it does take provisional data. It's not all final. It hasn't all been QA/QC'd, but there is provisional data in the database for about 600 federal reservoirs, about I think about a little under 400 on the Corps side and a little over 200 on the Reclamation side. And you can see throughout that plot of the addition of storage from the 30s through the 1970s into the 1980s. And the plot is giving you the cumulative storage available based on the most recent survey for every reservoir. And I make that point specifically to say that many of the reservoirs, as Tim and I were talking earlier, may have only a single survey, maybe back in the 1950s or 60s, and of course that shows an increase in storage. But if it hasn't been resurveyed since original, we don't see any reported drop in available storage there, which has a lot to do with why you see since 1998 things are pretty flat and static right there. We reached a total storage in this example of just under 300 million acre feet. Cursory look through the database shows that overall, if we take the whole portfolio there, only about a third of the reservoirs, maybe a little more, have had multiple surveys on them. So we're likely underreporting, we definitely are underreporting storage loss. So if we take the iCold global data, which was published, I think, back in 2009, gave an annual estimate of about 0.8% total storage lost globally. And if we're not reporting that, we're well below what we actually what this data is reporting. And so where are we? Are we somewhere back the same storage we were in 1968 or the 70s or the 80s? That actual number is a little bit elusive with the data we have, but what it does prove that the fact that we, with increased water demand and the maintaining of benefits that we'd all like to have, we have less and less storage to maintain those benefits with every single day. Next slide, Tim. So how do we develop a plan to get the maximum benefits out of a multi-purpose reservoir? Well, in general, it's only a viable reservoir if we have benefits that outweigh our costs. And in that case, those benefits there are 8 different federally authorized project purposes that it may be. But in general, there's a whole list of them right there. I won't go through each of them individually, but it's a wide range of different benefits, and each one of those has an economic, a social, a political, and environmental value to it. Next slide, please. And we have the original capital cost for construction, and then we have the costs associated with operations and maintenance. Those are known costs and costs we planned for. Then there were also those costs we didn't really plan for. Reservoir sediment management. In general, we'll talk here about the fact that the sediment management plan was to make them big enough in general in many cases that it was either, in the opinions of the developers, not a significant issue or a significant issue that would be resolved sometime in the future. We did not consider, we did not associate a direct cost with the storage loss over time or the aggradation above the channel or the degradation below the dam or the specific dam decommissioning. Those are all things that we talk about now that have a cost associated with them, which was not really part of the original equation. And then we have, introduce a term here, sediment design life. In most cases, the economic design life of these reservoirs to essentially pay them off was 50 years. And in many cases, the sediment design life is different than the economic design life. Could be 50, it could be 100, could be well more than that on some of these very, very large federal reservoirs. But much of the design was, estimate that sedimentation volume you think that you'll collect during that time, and then make an estimate of where you think in the reservoir that's going to deposit. And then in many cases, put the lowest level dam outlets above that level so that you don't carry any of those sediments downstream. Of course, that's as we look at it today, that's not a sustainable design. And what it did is simply by building the infrastructure that way, we deferred the future sediment management to a generation other than the generation that built the dams.
So another way to look at the sediment design life in more of an economic framework. So this is looking at costs and benefits. In this graph, we just have years, and it's just a schematic. It's more of a cartoon, if you will. Years prior to construction of a dam, these are negative. Construction of a dam here, and then going on out from 10, jumping off to 50 years well into the future. And so the red bars here represent the cost of planning, design, and construction of a dam. And then the blue bars up here above zero are the benefits derived from that project. And the green bars here represent the O&M cost of operating the project. And it's kind of subtle here, but there is a gradual reduction in the benefits because the storage is reducing over time. And eventually you get to the end of the sediment design life and you have to start, you can no longer ignore the sediment. Your outlets are becoming plugged with sediment and wood. You've got to start spending money. And then you get into decommissioning cost. And then you start the process all over again, except this time the best sites have already been taken. So as you look for building reservoirs at other places with population increase, land values are higher, permitting costs are higher, the sites aren't as conducive, but you begin again and go on. Another way to approach this is the sediment life cycle approach, where the beginning is similar, but you also start managing for reservoir sedimentation as you go. And then you just keep this going perpetually that way. Another way to look at this is through a longitudinal profile of a stream that's in balance. You put a dam and reservoir on a stream. All streams naturally carry some sediment, some more than others, but you begin trapping sediment in the reservoir and then releasing clear water downstream, which can be erosive. But one key here is you try to put the outlet above where you think the sediment's going to be over the sediment design life. And so it might look like this when the sediment design life is reached. And you notice that you get deposition at all elevations of the reservoir, but also that sediment begins depositing well upstream of the reservoir. A lot of people think that the sedimentation is confined to the reservoir pool, but it in reality is not. And Paul's got some nice slides on that later. And then if you continue to release clear water downstream, you'll often get degradation down below. Just another schematic looking at this. Here you can see the coarse sediments depositing at the upstream ends of the reservoir, usually sand and gravel, and then silts and clays would go on further down. And then if you let it go long enough, like San Clemente or Matilla dams out in California, you end up with a profile looking like this. Another example, Paonia Reservoir in Colorado. Here's this intake structure built 70 feet off the reservoir bottom. Here's a photo in 1961, and there's a person there and a person there. But then fast forward to 2014, now the sediment level is about 3 feet higher than that intake. So it's reached its sediment design life. About a quarter of the reservoir is filled with sediment now. These impacts happened long before the reservoir is completely full of sediment.
If we look at that, Paonia being a poster child for this without reservoir sediment management, the costs to mitigate or remove sediment when it's already deposited in the reservoir are considerably higher than either preventing it from getting into the reservoir in the first place or keeping it moving through the reservoir. And we'll talk about that shortly with a couple of examples. The costs are associated with that lost storage capacity over time, and then the direct impacts to the infrastructure itself. And those are in general items that we would repair and are easy to associate costs with, but are not generally considered sort of the baseline annual O&M. And those eventual costs, in addition, if we happen to have sediment impacts in the powerhouse, the lower left is a fairly famous picture in our group that Dr. Greg Morris took of a needle valve that had sand sucked through it for only about 24 hours, and shows that damage there in the second photo. We also have, the reduced value of recreation when we have deltas created with the sediment that's collected in the reservoirs. And then we have those upstream and downstream impacts, which are outside of the footprint of the reservoir, and so oftentimes don't fit nicely into that kind of O&M assessment there, because in many cases when large federal reservoirs were put in, the extent of the project is very, very close to the actual footprint of the reservoir itself, and so those upstream and downstream ones impacts are outside the project area in many cases. The upstream aggradation impacts, a couple of fun photos here. The lower left is myself standing in the middle of a reservoir that, as you can see, is approximately 6 inches deep. At the very head of a reservoir as the delta has formed, and that's what happens to your recreation when things don't quite go as planned. On the right side there is a fairly famous case study, at least within the Corps and Reclamation. This is the village of Niobrara, Nebraska, above Gavin's Point Dam. And you can see where Tim's got the cursor right there. You can see a couple square outlines. That's where the village used to be. And at the bottom there, in that half circle type city layout, that's where the village is now, relocated in the 1970s due to increasing groundwater elevations due to all that sediment you see deposited up at the top of the photo, which is upstream aggradation above Lewis and Clark Lake, which is behind Gavin's Point Dam. And then the downstream channel degradation, a couple of photos there specifically on the left. You get the vertical cut banks, exposed infrastructure, and the like, pipelines, telecommunications that come out of the water. And then if no management is ever viable, you have to remove and decommission that dam, and the costs that are associated with that. We've had a couple of moderate-sized dam facilities be removed. We haven't done that with any large federal facilities yet, but minus long-term reservoir sediment management, that day is eventually coming. And follow-up note: if you do need to decommission or look for another site, all the best sites are gone. The ones that have the best slope and the best valley shape and the like. And so if any resiting of new facilities needs done, the options are a lot less desirable than the original locations. And the long-term outlook is something I'm sure everybody understands. Many of us have seen the classic plots of the increase in global water demand and the reduction in reservoir storage, of surface water storage, out of a number of different texts, and that we lose according to that iCold data, worldwide, almost 1% of that total storage every year across the planet. And if we're losing 1% per year, and we compare that to a growing population, we've got a concern on our hands. The very climate variability is a wild card in all hydrologic systems. Also, so in reservoirs, if we have more intense storm events, almost watersheds that become more ephemeral, we know that the vast majority of sediment is transported into reservoirs, and those very short but high intensity storms, if we have more of those, the long-term outlook for our storage availability and water supply can change. And then we look at some solutions. We're going to go over this generally fairly quickly, because Dr. Greg Morris did a webinar last month with some really neat like case study examples of how a lot of these management techniques work. So we won't go too deeply into them, but in general, a neat graphic here that shows 3 different general categories of managing sediment. The green ones are preventing sediment from getting into the reservoir. Land management, check dams, other methodologies for keeping the sediment in the watershed. If we can't keep it in the watershed and it enters a reservoir facility, the next best option is to keep it going, not allow it to deposit in the reservoir. Diversion weirs, bypass, drawdown, sluicing. If you have a large flood event coming into the reservoir, can you manage and regulate your reservoir so that much of that sediment continues to move through the reservoir and out the gates instead of depositing? Or if it does deposit, we look at what are consistently the most expensive options, which is to physically remove it in some way, whether that be through mechanical means or draining the reservoir and causing extreme erosion of the delta through a flush and moving it down. So those are the 3 general categories when we discuss sediment management in reservoirs. And in reducing that sediment inflow, we can do grade control. We can reduce soil erosion. Anything we can do there to keep sediment in its place, or if we can't keep sediment in its place, capture it before it reaches the reservoir, if we can find some other use for it or some other way to manage it above the reservoir. If we do have to handle that sediment in the reservoir, how can we keep it moving? When we deal with fines in many parts of the world, monsoon type runoff creates essentially what would be considered like a thin pudding type of sediment that's a fairly high concentration, that because of its density travels along the bottom of a reservoir. And if we have the appropriate infrastructure, we can allow that, what's called a turbidity current, to plunge to the bottom of the reservoir and move along it, and then be vented or discharged through either gates or tunnels or something at the bottom of a reservoir. That is a technology that's not real common in this country, many times due to the fact that most of our reservoir systems are, highly alluvial. Drawdown and sluicing. The implication here is that if you have some sort of event that's bringing quite a bit of sediment in, if you have the flexibility to do so, opening up the gates of your reservoir to allow that high sediment concentration flow to continue through the reservoir and out, is definitely beneficial and can significantly reduce the rate of deposition in the reservoir. And a major modification would be what they call a bypass tunnel. In many cases, if you have the right shape of the valley in your watershed, you may be able to pull off high sediment flows before they get to the reservoir and divert them either into an off-channel reservoir storage to trap sediment, or to put them in a channel or a tunnel to send them around the reservoir and reintroduce them to the downstream channel below the dam. Now, if you can't, one way or the other, if you can't do any of those other things, we're stuck with managing the sediment after it's been deposited in the reservoir. Flushing is a common methodology used to do that, and flushing usually works the best when you have low-level outlets and you have a lot of head and you've got a lot of flow. That, of course, limits it to not every reservoir. Its efficiency or its efficacy will be highly variable depending on the plan form of your watershed. This is a couple of pictures of Spencer Dam in northeast Nebraska. The one on the left showing sediments eroding from a drawn down reservoir, and on the right, those sediments being discharged down through the open gates into the downstream tail race there. If a flush won't work, either you don't have the head, or you don't have the hydraulics, or you don't have the right material, or something like that, really the last option here is to get in there and remove it physically, either dredging or dry excavation, pipe it, trunk it, truck it, however you need to move it. That's kind of the last option for sediment removal. Ideally, you'd love to reintroduce it downstream, hopefully to mitigate some of that downstream degradation. But one of the big limitations, of course, in managing this way is finding something smart, cost-effective, and environmentally responsible to do with sediment, because in many of these cases, the amount of sediment we're talking about is just, it's not feasible to use any sort of, say, settling pond or disposal facility, dewatering pond. We have to find either a beneficial use for it, or we've got to find a way to reintroduce it to the downstream channel while mitigating any of the impacts that might have. And then we'll switch here a little bit, take a little different tack to talk about, we've talked about the problems and kind of where we sit, and that's all well and good, but as Tim and I sit on our pulpit here and talk about all these problems, we need to talk a little bit about what we're trying to do to address these problems. So here's a few current federal activities that are going on between the agencies, some of them jointly, and talk about the progress that's being made. First, early on, I showed a slide of the RSI Reservoir Sedimentation Information Database, the sediment surveys. We need to continue to update that and make progress on that. A little bit about the Corps' Regional Sediment Management Program and what it's trying to do. A few pilot projects, research, and then a few innovative prize competitions, and then what the SOS and the Reservoir Sedimentation Sustainability Team are currently, what their current actions are. Oh, and then the SEDHIDE conference. We wanted to put a plug in for that, and we'll talk about that too. So here's just a splash page of the RSI database. the Response to Climate Change program under the Corps of Engineers initiated a couple years ago, and is still working towards getting a final product. A little over a year ago, developed a partnership with Reclamation to get their information in there. And you can see in the lower right, there's 221 reservoirs complete, another 300 plus in the process of QA/QC, and then another 100 and plus that we're still efforting to get data through. And we also have an ongoing project right now within the Corps to essentially archive any ongoing sediment management at these reservoirs, so that we could look at what are the sediment impacts, and is there anything being done about that. So that's an ongoing process with that database. And the Regional Sediment Management Program, or what we call RSM in the Corps, started as a demo project, gosh, almost 20 years ago now, on the navigation side, to look at, what's a better use for sediment, instead of just the traditional pump and pile in navigation channels. Why don't, where can we find a better use with more benefits to sediment? And it started there, but it's grown into a program that many of our inland districts are participating in, and fortunately we're really trying to take a watershed. It says they're a systems approach, and so from the watershed to the mouth, navigation to all the other project benefits. How do we manage sediment smarter? One, create more benefits where we have it. And two, supplement or reduce the loss of benefits where we don't have it. And that program, the RSM, has stood up over the last 2 years with a little sub-program we call RSMU, or RSM University, where that program is supporting a set of workshops. Not just on these, they support other workshops on thin layer placement and dredging technologies and coastal engineering and the like. These are the two that really apply to us here on the reservoir management side. I did one for planners, managers, and regulators last year. As we begin to manage reservoirs, the regulatory side of it is a little bit of the Wild West right now, and we're having to learn as we go. And then in this 2018, we'll do a reservoir management workshop for engineers that's a little more, analysis, a few more analysis metrics involved, including some modeling and such. And the last one I'll talk about here is a couple of these pilot projects. Section 1122 of the current WRDA called for the Corps to develop 10 pilot projects on beneficial use of dredge material. That it's kind of framed generally in the sediment navigation channel side, but I know that we have a number of proposals that were put in there about beneficial use of reservoir sediments. So something may come of that. The Corps of Engineers, our office here, and Tim's office are partnering in a pressure flush analysis and collaboration out at Cherry Creek Dam and Reservoir in suburban Denver, looking to use that pilot study to learn what we can about the influence and the magnitude of different pressure flushes. And a pressure flush is where we keep the pool high. We just open the gates, create a small cone of influence with increased velocities around the gates, and essentially suck out some sediment right in front of the gates. It's occasionally used as a management tool on some older reservoirs, and the project will hopefully look at how we could expand that and how we could estimate what the impacts of such action might be at other reservoirs. As an RSM project, we did a drawdown flush modeling at Spencer Dam in Nebraska. And we did the modeling there to see if we could get a HEC-RAS model to replicate what the reservoir was doing. Tim, I'm going to take control of the desktop here, and Tim, can you confirm that you see the screen
Yes,
now?
came right up.
Okay, perfect. And I'll note to everybody, this looks choppy because it is. It's a time lapse of about a day and a half. This is Spencer Dam. And what you're seeing here is a small reservoir, originally about 20,000 acre feet, now about 1,000 acre feet, being slowly drawn down. There's a real-time clock right below the image there. And what this is going to show is simply some of the physical impacts of a drawdown flush. And we'll take about a minute here to look through a couple sections here. In just a few minutes, they'll open the gates all the way, and you'll see there goes a fairly extreme head cut working its way and eroding sediments right up that channel that's on the left of your screen. This reservoir flushes twice a year. It gets to about 99% full of sediment, and they flush it for a couple of weeks, and it goes back to about 95% full of sediment. You can see the bank eroding on the right side there, as this head cut will continue for the rest of this day. And then I'm going to hop forward here a little bit. I apologize, a little too far. On the right there, you can see another channel cutting in late in the afternoon. As the three channels of this river kind of flop back and forth through the reservoir, and as with any flush, you get the most of your heavy lifting done in the first couple of days. This is showing the first day and a half of a 4-week flush in order to get much of that sediment out. And you see as the sun setting where the channels are, and we come back the next morning and that channel on the right is perched. It's now way off to the right, but we're still eroding material in the cut bank right in the center of the screen there. So this is just kind of a neat example of what happens in a reservoir flush, and it also shows how highly unpredictable it is, because I went to 2 of these and the response, the river response and the erosion response were very similar both times. And then I took one of my cohorts up there, Dr. John Shelley from Kansas City, and I stood out there and I said, now this is what's going to happen. It's going to cut right down on the hard left here, another channel on the hard right, and we watched it, and wouldn't you know it, the channel came right through the middle. Not at all where anywhere I had seen it go before. So that's one of the ongoing challenges with this, is trying to model and estimate what these are going to do. Tim, do you want to go ahead and pull that back, please? And that reservoir is still actively flushed twice a year. It is that the powerhouse on that facility is being decommissioned, so they are working on a long-term water management plan to assess those impacts. Quickly here, one of the other things we're doing is research numerical reservoir modeling with RAS and ADH, adaptive hydraulics. That's a 2D package supported by Coastal and Hydraulics Lab out of Erdek, Vicksburg. In both those products, the Corps continues to develop functionality to make reservoir modeling simpler and more accurate, and the like. And those efforts have been going on for quite a while, and we continue to model more reservoirs in those software packages to test them and see how well they do.
So here's another example of research, and this is work from Dr. Young Lai, who works for Reclamation here in Denver. But here he's developed a three-dimensional sediment model to simulate the passing of turbidity currents through a reservoir. This happens to be a reservoir, Shimen Reservoir in Taiwan. But what you see here is after 1 hour, the sediment coming in, diving along the bottom. This is a turbidity current. This is what it looks like after 4 hours and after 7 hours. And so this idea is to help figure out, can we vent the turbidity current out through the dam? Where might we need to install new outlets to be able to do that? We're also working on a research prize competition. We'll have our design kickoff meeting this afternoon. But we're looking at better, more efficient ways for removing sediment from reservoirs. We're offering cash prizes to citizen solvers who can identify newer improved techniques for reservoir sediment removal, either the collection, the transport, or discharge of sediment. And it's an interagency team, Reclamation, Army Corps of Engineers, Natural Resource Conservation Service, Federal Energy Regulatory Commission, and we're also looking for some non-federal partners as well. I'll talk just a little bit about the Subcommittee on Sedimentation. That's this interagency committee. It reports up through to the Assistant Secretary for Water and Science in the Department of the Interior. It's comprised of federal agencies, NGOs, and university research organizations with the aim of fostering agency, university, and industry collaboration. Some of our activities of this RSI database used to be called ResSed. Now we've just produced dam removal analysis guidelines for sediment, managing infrastructure in the stream environment. Joel Schultes and Carolyn Ewing were some of the lead authors on that. Resolutions and position papers, and the National Reservoir Sedimentation and Sustainability team, which is the group bringing you these webinars. And this team is comprised of volunteers from agencies, universities, consultants, and industry. The team provides short courses at conferences and also these webinars. We have a list of frequently asked questions and the answers to those on our Subcommittee on Sedimentation website. We are in the process of formulating a white paper and providing guidance on reservoir sedimentation monitoring. In regards to the resolution, this is a resolution that was passed a couple of years ago. It's encouraging all federal agencies to develop and implement sustainable sediment management practices for their reservoirs that they own or operate, or come up with the retirement plan for those facilities if we can't figure out the sustainable practice. I should also note the U.S. Society on Dams has adopted pretty much the same resolution, except instead of for just federal agencies, for all owners of all dams to do this. And federal agencies are encouraged to start developing some of these sustainable plans now for 1 or 2 reservoirs per year on a pilot basis, and then getting us better geared up for the future and doing more of these at a faster pace. And then the future planning studies would have to address the engineering, economic, and financial feasibility of potential sediment management actions, which would be necessary to maintain the existing project benefits. And then the SEDHYDE conference, that's Sedimentation and Hydrologic Modeling Conference, that used to be a federally sponsored activity, or at least hosted activity. Now it's going to be hosted by a private nonprofit, but it'll have topics like sediment measurement. I'll let you read through this, but one of the key ones is reservoir sediment management. And that'll be in June of 2019 in Reno. And so the reservoir sediment management strategy for most federal reservoirs, or at least large reservoirs, would probably have to focus on managing recent or future sedimentation rather than past sedimentation. The idea of going after decades of past sedimentation is likely going to be cross-prohibitive, except in small reservoirs. And so the best you could probably hope for is to keep up with what's coming in. John Redmond Reservoir in Kansas, they dredged a volume equivalent to 3 years of sediment supply, and they took a 20-year bond to do that. So it's a step in the right direction, but it'll have to probably focus on what's coming in and then manage that sedimentation each year. The idea of getting in and getting out on a one-time basis is probably not going to work for the larger reservoirs. You'll have to do it every year. And then over the long term, sediment is going to have to pass downstream or supply other beneficial uses. So those beneficial uses could be soil augmentation for agriculture, land development, construction fill, concrete aggregate, wetland or other shallow water habitat creation, shoreline beach development or augmentation, and then, of course, offsetting downstream channel incision. And so sediment continuity is important. If the dams and reservoirs weren't there, all the sediment would be passing downstream. So allowing sediment to pass downstream may slow, stop, or reverse the downstream channel erosion and degradation that's been going on. And over the long term, sediment management cannot be allowed to overwhelm the downstream channel. And so we have to be careful about that. And then some deposition downstream may be acceptable as long as there's not unmitigated harm to people, property, or native species. And sediment going downstream may help native species, but it could harm introduced species. For example, the endangered humpback chub and other native fish in Grand Canyon evolved under very turbid conditions and use turbidity as cover from predators. And a big need for sediment monitoring. The first obvious sign of a sediment problem may be the plugging of a dam outlet or reservoir water intake with wood and sediment. It's a lot like cholesterol building up in your arteries. There's no symptoms until you have the heart attack or stroke. In this case, it's problems with the outlet or some other structure along the reservoir. And reservoir surveys are periodically needed to monitor and forecast problems and avoid the crisis management. Reservoir survey costs have substantially decreased over the past few decades, while the quantity of data has dramatically increased. My first survey in '82 was 3 boats and 9 people getting data points every 25 feet along a line space 300 feet apart. Now with survey grade GPS and multi-beam depth sounders, we can get many, many more data points, thousands more with less personnel at less cost. There are also surrogate technologies becoming available to continuously monitor sediment into and out of a reservoir, and these can continuously measure. So this technology is being utilized more. So getting into our conclusions, monitoring is now more important because most reservoirs are in the second half of that sediment design life. A decade or more may be needed to plan and implement sustainable sediment management plans. And no action will eventually lead to the retirement of the dam and the reservoir. And conclusions, the cost and impacts of reservoir sediment management need to be compared against the eventual cost of retiring the reservoir and the cost of constructing additional water storage elsewhere. A lot of people think this is just too expensive, but then if you look at the cost of losing those reservoir benefits and having to build it elsewhere, then it doesn't look so expensive. And future generations should be considered when choosing a reservoir sediment management plan. And sustainable sediment management may harm introduced sport fisheries, but keep in mind those reservoirs can't trap the sediment forever. At some point, once those sediment level gets to the outlet, sediment is going to start going through, and folks that have depended upon having clear water from dams, that can't last forever. And so releasing sediments at a point downstream of a valuable fishery may be another method to avoid impacts. So with that, we'll open it up for questions, and I'll turn that back over to you, Toby.
Okay, thanks very much, Tim and Paul. Great talk. We have had a number of questions come in. I think what I'm going to do while I'm sort of organizing these, and the folks that are listening in, feel free to keep sending over questions as you have them. The first question, I'll ask this one. So either Tim or Paul, either one of you can answer this. So why aren't damages attributable to sedimentation and scour not considered in the benefit cost analysis?
Well, I'll take a quick stab at it, and Paul, you can certainly chime in. I think when folks were doing the economic analysis, they used the discount rate. And so when the dam is brand new, any kind of impacts or costs that'll happen much later when you apply the discount rate in economic theory, it just doesn't make any difference to the present value. And so whether they consider them or not, when they discounted back to the present value, it just doesn't mean much. Like $100 impact 50 years from now is going to be worth $5 today.
Okay, thanks, Tim. Here's another specific question here. Was the town in Nebraska upstream of the reservoir originally located in the flood pool, or are these types of impacts exceeding reservoir boundaries?
In that specific case there, that's the village of Niobrara is about, I want to guess, over 10 miles above the normal full pool of that reservoir downstream. That one's a little bit of a double whammy because one, you've got the sedimentation effects due to aggradation upstream from the delta in the reservoir below it, and it's also exacerbated by the fact that there's another dam above it. So any high or flood flows that used to clean sediment out going past that village are no longer there. And in that case, you've that delta has really grown 5 or 6 miles into the downstream reservoir, and it's grown about 10 to 15 miles above it. But yes, it's between two federal projects, but not in a federal project.
Okay, thanks, Paul. So there's a number of questions here about collaborative and support programs and sort of just general information. So either, I guess this will be directed to either Tim or Paul. The questions are about where to find the best resources for sediment modeling and management. I have a feeling I know what you would say, Tim.
Well, we do have models that are you can download for free from our website. However, they're mostly focusing on the hydraulics and the sediment modeling part. We have internally, we just haven't had time and funding to produce the manuals for those yet. HEC-RAS, though, that's widely available. Paul, do you want to speak to that?
Yeah, certainly. You know, we in the Corps and primarily the Hydrologic Engineering Center in Davis have been actively looking to find new places, new reservoirs to model, as it were, and looking at the integration between that and SWIMS and ResSim as it manages flows and the like. So on the modeling side, yeah, HEC, the Hydrologic Engineering Center, and the Coastal and Hydraulics Lab, and I'll put another plug in for the Regional Sediment Management Program, which does through all the projects that are created from it every year. They publish Corps of Engineers tech notes on all of those, on all these new creative uses and best management practices that they're trying to implement. So back on the slide, we had a few slides ago where there was an RSM web link. If you go to there, you can see everything that program has published. And then on the website for the Subcommittee on Sedimentation, there is information about what the National Reservoir Sedimentation Sustainability Team is doing, and you can again get your hands on all those white papers and those actions that are going on with that federal committee.
Great, thanks, you too. So there's a couple other questions here about just general monitoring questions, mostly about sediment, but also probably about water quality in general. And I'll just use this as a plug to say that on May 10th, I believe, we've added another webinar that'll be on reservoir sediment monitoring. That'll be given by Greg Morris. So I'm definitely tuned into that. I think Tim and Paul, you kind of covered that a little bit, so maybe we can leave that there. Another sort of related question is a couple of questions about permitting. A question about what permits will be required for the sediment sluicing, and then how to manage when you have multiple reservoirs in line. Just a note about that next month on April 26th, our next webinar, that will be given by Dr. Roland Hotchkiss, who will be talking about permitting. So, but Tim and Paul, do you want to talk, do you have like just a couple minutes you could talk about permitting?
I will say that through our national team and our subcommittee on sedimentation, we have drafted a position paper that's awaiting approval by the advisory committee, but it's basically calling on federal permitting agencies to make a path forward to achieve permits to do this kind of thing. It can be difficult, and I know that Roland Hotchkiss, who's going to present that webinar on permitting, has had some personal challenges in trying to get permits. And I think it's sort of a newer topic to the regulatory agencies and how to deal with this, but I think it's going to be becoming much more commonplace in the future. And as I said previously, the reservoirs can't trap sediment forever. And you either allow sediment management now or eventual decommissioning of the reservoir, but the idea that the sediment will never get downstream may not work out very well.
I would follow that up just quickly in saying that, you know, over the past few years, there have been a few reservoir management permits issued. You know, and they're few and far between at this point. And, you know, the regulatory office within the Corps at each different state has to undertake determining what the requirements of that permit are, and if there are other federal partners, if there's endangered species, fish and wildlife, there are clean water certifications from the states, and all of that. There was some basic guidance, a regulatory guidance letter authored over a decade ago now in the Corps that lays out a basic framework. It talks about some maintenance exemptions and what is considered a permittable discharge and whatnot. But it is tricky because you can very well, you know, two different states might take a different approach to how to put stipulations on the permits and such. So you know, we're compiling case studies and examples right now, which is literally about 10 of them or so. And again, Dr. Hotchkiss will share some neat examples, and we've got 3 of them going on in our district right now, in the Omaha district we're trying to work through. So we're just looking to reach that critical mass, and hopefully there'll be a point where we can start putting some standardization in the permitting process. But a lot of the endangered species and state requirements do make it very, very site specific in many cases.
Great, thanks, you too. So I think we have time for just one last question here, and it's related to the one that you were just answering, and it has to do with just what the federal perspective means. And I think you did a nice job of covering that, what that means, maybe in the, you know, from the viewpoint of the subcommittee on sedimentation and trying to get sort of understanding across multiple agencies, and in particular with relation to various federal agencies and states. But I don't know, could you say, I mean, maybe could you talk a little bit about the federal organization and the perspective from the feds relative to, you know, how this might actually play out in a local site setting?
Well, Paul, maybe you could talk about that in the context of the reservoir sediment management program you've got within the Corps.
Well, yeah, I mean, you know, sustainability is one of those the efforts that the Corps and all federal agencies are undertaking, and I think the big crux from you know, the Corps standpoint is how do we balance the long-term preservation of these benefits against our authorized project purposes. You know, there's a general public understanding that these benefits, now that they have been established through the construction of these projects, are fixed and static and will be there forever. So I think it's imperative that through whatever program, through RSM or through the climate change or through headquarters sustainability program, that we begin the process of examining what are the trade-offs of these benefits, and instead of just looking, you know, 1, 2, or 3 budget cycles. You know, everybody cringes when you say, what's it going to be in 50 budget cycles? But planning for just next year, in a sustainability framework doesn't give us the appropriate time horizon to really look at impacts and the change in benefits and stuff. So I think that's one thing we're wrestling with is how do we look so far into the future to really quantify that loss of benefits, and then what are we willing to do? How much action are we willing to take to preserve those benefits?
Great. Okay. Well, thanks everyone. Thanks everyone for tuning in. Just a quick plug that our next webinar will be April 26th on permitting with Dr. Roland Hotchkiss. And we should have this webinar recorded version up on the web here in the next week or so. And also the professional development hour certificate. So definitely look for those. With that, I'll end. Thanks to Tim and Paul for giving a great talk.
Well, thanks, Toby.
Yes, thank you very much.
Take care.